So I'm going to talk more about Markov chain Monte Carlo sampling and some other things. This is something that I can talk about forever, and so we won't do that. I'll try to finish. No, we'll definitely finish, and hopefully I'll say some useful things. So I think, so Megan got you appropriately frustrated this morning, I think, with, you know, how much of a pain it was to do MCMC. And I'm not going to solve that. So, you know, get ready for more of that. That's sort of part of this life. But when I sort of the point of this presentation and then the tutorial that I prepared for after is to teach you some of the tools that are commonly used for doing MCMC for research. So most of the time, you're not going to use the Metropolis Hastings sampler that you wrote yesterday and worked with today. There are some cases where it does make sense to use that or to use you know, some custom-built sampler like that. But for most research applications, it's actually going to be better to use some software library that was developed for doing MCMC. And part of that is just to make the process of setting all the tuning parameters and doing the convergence tests and that kind of stuff, to make all of that flow a little bit smoother, because that is a big part of what goes into doing MCMC. So yeah, so I'm going to talk about 3 different libraries that all implement different algorithms. And then in the tutorial, you'll get an opportunity to use all of those and to sort of see how they fit together and stuff like that. And I'll go through, again, this is one of these things that we could talk forever about. So I just be, you know, sort of from a theoretical standpoint, I'm going to give a pretty surface level introduction to what's going on behind. Hopefully, it'll be enough information that you can, you know, sort of BS your way through explaining what it, you know, that's what I spend my life doing anyways, and say the right words or know what to Google. But something else I was going to say. But I'm hoping that you will get a sense of how to actually use them in your work. So yeah, so hopefully that'll all come together. To start with, I wanted to say a few more things just to emphasize some of the things that Megan said this morning, just so that we're sort of on the same page for motivation. And the first one that I think she said, but that I really wanted to emphasize is that Bayesian inference and MCMC, the reason why you do it is to do integrals. The only thing you ever do is integrals. That's the entire story. And the integrals that you want to do have some form like this. Where D is some representation of your data. This is the posterior probability. Theta are your parameters. And you want to evaluate some expectation of some function of your parameters weighted by the posterior probability. This is it. This is all of Bayesian inference, and in my world, it's basically all of science. So MCMC is a way of doing this integral. It's, you know, we say lots of other words, but like at the end of the day, that's all it is. That's all what it's all about. And the way that we do that is by approximating this integral as a sum let's call it n, where it's a sum like this, where these theta n's are samples from our posterior probability density. So that's where the relationship between doing integrals and sums are. And the key thing to see about this, so if you're willing to believe me that the only thing you ever want to do is an integral, and an integral that looks like this, then the key thing to realize is that this approximation that I've done right here, the error bar on that approximation, because there's going to be some numerical noise associated with approximating this integral as a set of samples, it scales like, so the error on this, the Monte Carlo error, is proportional to 1 over square root of n. So as you get more samples, your estimate of this integral, which is the thing that you actually want to do, scales like that. So you get more samples, and your error bar gets smaller, and we all get happy, right? Now, something that you noticed was that we were making those autocorrelation plots earlier, and neighboring points in your Markov chain weren't independent. And the reason why we were looking at those plots was because the n that goes in here isn't actually the same n as this one right here. The n that goes in here is the number of independent samples. And so that, in general, with an MCMC will be much smaller than n. So if you run 100,000 steps of MCMC, that doesn't mean you have 100,000 samples. You have some smaller number of samples, which is the effective number of samples. And the way that we would compute that would be by looking at these autocorrelation plots and computing the integrated autocorrelation time. The integrated autocorrelation time is the number of steps you have to take before you get an independent sample. And so when it comes down to MCMC in practice, what you want to do is you want to get the largest number of independent samples with the least amount of computational time, more or less. You might also want the least amount of your time, and so that will be a factor that plays into our discussion as the day progresses. But really, sort of in an ideal world, you want more independent samples for less computation time. And so what that means is that you want to decrease the integrated autocorrelation time. And so what I'm going to talk about today are all of these different algorithms for doing MCMC. And those will have different behavior. They'll sort of have different autocorrelation behavior depending on different problems. And so they'll be better for certain problems, and they'll be more efficient for some problems and less efficient for other problems. And part of what I'm hoping to give you today is just a little bit of intuition about when you might want to use one or the other. Okay, does anyone have any questions at this point? And please feel free to interrupt me at any time. This is your lecture. I have tons of notes, but I'm happy to adjust as necessary. Yes? Can you turn on the microphone? Again? Right. So the question was, what in this integral, what is f? And I blew past that, and so that's a great question. And so f is any function of your parameters. So for example, if you want to, one thing that you might want to estimate is what is the expected value of one of your parameters? Like, what's the mean value for that parameter under your posterior? In that case, you would have f of theta would just be theta 1, if you wanted to know what the expected value is for parameter number 1. Similarly, if you wanted to know the posterior variance on that parameter, that would be a different integral, where this would be something like right? And so if you think about it, you can end up sort of figuring out what integral you want for all sorts of, for basically any question you're going to ask. Adam asked me to mention the word credible interval or credible region. That would be another integral that you could do using samples like this. And there, what you're looking at is what is sort of what parts of parameter space are within a certain amount of probability. So a common thing to do would be to find the 16th and 84th percentile of your 1D probability distribution. And that would give you some bounds on the expected distribution of your parameter. And that's all something you can compute as an integral that looks like this. Any other questions? Great. Okay, so I think, so what I wanted to do now was I wanted to move on to sort of talking about the specific methods that you, or the specific libraries that you might use for doing MCMC. And hopefully with some practical suggestions in there. Oh, I guess actually maybe I can do this. There we go. As a staff member here, I don't get many opportunities to lecture on a board, so this is really fun. So the three different packages and algorithms I want to talk about are first a package called MC, which is something that I wrote, so you get to hear about it. And the algorithm that's implemented in there is an ensemble sampler, and I'll get into that a little bit. It's widely used in astronomy. Some of you might have used it before. So then the second one I wanted to talk about is kind of a new kid on the block, but it seems really awesome, and it's called Dynasty. And it implements something called nested sampling. And it is not an MCMC method, but it can be used for a lot of the same purposes. And I'll get to that in just a second. And then the last one I want to talk about is PyMC3. And it implements something called no U-turn sampling. And it's very exciting, and I'll get into more details about that later. But I had something I wanted to say about that. Oh yeah, so there are many other options. I've chosen 3 here. There are lots of other things, and you're welcome to use other things, but I chose these 3 because they're the 3 that I've used most, and that they sort of span the range of things that are available to some extent. So they'll give you some sense of sort of the types of things that are available. Good. And so now I want to go into a little bit of detail about each of these, just to give you some idea of what happens behind the scenes. First off is MC. Let's see, I'm going to leave that up there. And so I'll talk about the algorithm and the interface a little bit, but first I wanted to say, so one of the sort of fundamental design decisions in MC is that it's designed to work with a black box likelihood function, or a black box log probability function. And so that's very useful for astronomy. So some of you might be familiar with, your advisor hands you their advisor's Fortran code and says, fit this to some data. It has some parameters, init files, and all that kind of stuff. And so MC was specifically designed to be able to work, with those kinds of models. And I think that's one of the reasons why it's been used in astronomy quite a bit. That won't be true of everything that we talk about. But the basic idea with MC is, let's say we have some, say, two-dimensional parameter space. Our parameters are theta, and we have some posterior probability density here. I'm drawing sort of contours to represent where that would be. With Metropolis Hastings, you would have, you'd start with your point somewhere in parameter space, and it would walk around, and you'd have some proposal, maybe a Gaussian, that would tell you where to move based on where you started. And that can be a problem with a posterior that looks like this, because you would need to tune the proposal in your Gaussian to be aligned with this axis right here. So if you were right here, let's say if you were right here, you would want your proposal, they even have different colors. You'd want your proposal to maybe be something like this. You want it to move along the axis of the probability contours, right? And it can be, kind of annoying. In 2D, it's not so bad, but as you go to higher and higher dimensions, that can get tricky to tune. And so the basic idea with MC is to reduce some of that load, and instead of just having one sampler that's moving around and making little moves, you have a bunch of them. So you would have lots of samples all over. And then if you're trying to move this one right here, you would move it based on the positions of all of the other samplers that you have running in parallel. So in MC, we call those walkers. So you have this walker would move based on the location of all the other walkers in the ensemble. And so that's where the name ensemble comes from, because you have all of these walkers working together. And the thing that's nice is that, they're all sampling the probability distribution. So that means if there's a correlation like this, they'll be lined up in exactly the way that you want to move. And so roughly the way that it works is, let's say I want to move this one. What I would do is I would choose one of the other walkers. I would draw a line between them. And then you're going to move along that line. And there are various choices that you can make about how you move, but essentially most people use the default, where it can move between halfway between them to twice the distance between them. And you'll see that, that's exactly the line that you would want to move along to get an efficient proposal. And so this is nice for astronomy applications. It means that we always have correlations. We always have astronomers use insane units, right? So everything, the dynamic ranges are all weird. And so it can be, this thing is insensitive to all of those kinds of, all those kinds of issues. But then otherwise, more or less, it's the same as your Metropolis algorithm. It starts with the ensemble one place, it updates all of the walkers, and you get correlated samples, and you have to look at the autocorrelation function of the positions of the walkers and that kind of thing. And so all the same sort of convergence diagnostics that we talked about this morning are things that you'll want to look at when you're using MC. Yeah, please, can you use the microphone?
Do you predefine the distribution of the walkers?
That's a great question. So I was just about to get to that. So that is, so everything that I've said here looks really nice when all the walkers are in the right places, right? But that's sort of circular, right? Because that's the whole point, is we want to get there. And so this is one of the big things about using MC, is that it's very important that you have a good initial distribution. And there's nothing in MC, the package, that helps you with that. That's up to you to do. And so, for example, you can imagine if you put if you started all the walkers over here in a tiny little ball on top of each other, it's going to take them a really long time to get over there, right? And so you can imagine that the burn-in would be bad. And in fact, that is something about MC, is that burn-in in general is more egregious and longer than you would get with Metropolis Hastings. But once you're burnt in, then things are pretty sweet. But you're absolutely right. The initialization really matters. And if you could initialize them perfectly on top of the density, then that would be ideal. So in practice, what I normally do, which isn't necessarily optimal, but it tends to be a good starting point, is I actually use an optimizer like you learned in the tutorial this morning. And I would like try to find something close to the peak of this. It doesn't have to be great, but somewhere in the vicinity. And then I would actually initialize all my walkers in a fairly small ball around here that I hope is sort of smaller than the typical scale. Because in practice, I've found that it's much easier for the distribution to expand than to contract. So it might seem like you might want to start with them everywhere and shrink down. But I've found that in practice, that can be much harder to do. So the way that I would normally go about starting MC would be to start as close to the optimum as I can find. Yeah.
So this is kind of a minor detail, but just out of interest, do the walkers update relative to the, do they update simultaneously, or are they updating like in some sort of sequence?
Yeah, that's a great question. So so the question was, do you can you update all of the walkers in parallel, or do you do them one at a time? And the original paper actually derived them updates one at a time, and it's easy to prove the reversibility and detailed balance that you need for a valid MCMC move in that case. In the MC package, we actually leapfrog it. So we update half of the walkers based on the current position of the other half, and then we update the other half based on that condition. And it turns out that you can make the same proofs in that scenario, but it lets you update at least half the ensemble in parallel. And so that's one of the benefits, is it lets you parallelize your calculation of the log probability function, because remember, every time you move a walker, you're going to have to evaluate that function. And so if it's expensive, it's nice to run that in parallel. Great question. Yes?
What does it mean that you update the position of half of the walkers depending on the other? Like, what is the condition?
Oh, yeah. So the way that it worked was, when you update this guy, you randomly choose another walker from the complementary ensemble, which is anything that's not within the same subset. So what I mean by that is that, so I would fix the position of half of the walkers, and the other half would each independently choose a random walker from the other half that aren't currently being updated, and then update them with the MC move. So after one proposal, half of your walkers will still be in the same place, and then you would update these ones based on the coordinates of these ones. So does that?
I think my question is more, like, is it dependent on the position? Like, do you avoid some region because there is a walker there? Or
Oh no. So every time the update always is a pairwise operation. So if I'm trying to update this one, I would draw the axis between those two and perform a sampling along that line. And then the point about splitting it in half is that the sort of helper walker has to be drawn from the set of walkers that are not currently being updated. Because you could see how there might be a problem if at the end of the step this one was now in a different place, then you no longer have a reversible move.
Okay.
Great. All right, so that's good. Any other questions? Good. Yeah. Oh, yeah.
Do you run into issues with like multimodal parameters where maybe one walker is stuck in one and another walker's in another, and if they try to move to each other, they end up spending time in the middle, whereas that might not be realistic.
Great. So the question was, what happens if you have a multimodal distribution? Your helper walker is in a different mode than the walker that you're moving. And that is bad news, right? Because you're still doing an accept reject step that is similar to the Metropolis Hastings accept reject. And so if let's say we have a 1D posterior that kind of looks like this, and our one walker is here and our other walker is over here, your proposal is mostly going to be in regions that are very low probability, so you're not going to accept them. And so it doesn't make the algorithm wrong, like it's not going to spend more time than it should in between the modes, but your acceptance fraction is going to plummet. And in fact, this is a really big limitation. So MC really struggles with multimodal distributions. Whereas Metropolis, it wouldn't be so bad. You just like move around in this one and you never find the other one. With MC, it actually just grinds to a halt and like everything shuts down and it's really bad. So no, that was another a really important point. So it tends to help to think about if you can sort of reparameterize the problem so that you get rid of degeneracies that look like this. And there are various options for dealing with that, but yeah, it's definitely going to be a problem if you have something that looks like that. Any other questions? I want to see if there was any other. Okay, so in practice, MC is pretty straightforward to use. The main tuning parameters are the number of walkers and where you start. And the performance is sensitive to those things, but they're sort of sensible things that you can do most of the time. And if you don't have a multimodal distribution, if you have something that's reasonably well behaved, even if there are crazy degeneracies, you can get pretty good performance with MC up to about a dozen parameters, which is okay sometimes. But if you have more than a dozen parameters, you're going to have to be super patient. It can take the autocorrelation time can be very long, and it scales very poorly with the number of parameters. So if you have 100 parameters, it's going to be you better fire up the supercomputer and settle in. Good. Okay. Way too much time, but great questions. So this point about the multimodal thing brings us really nicely to the next algorithm that I wanted to talk about, which is nested sampling, and it's implemented in this Dynasty package. And basically, the idea there is so nested sampling is an algorithm. I said it's not MCMC, and the key point is that actually the thing that nested sampling tries to evaluate is specifically designed to evaluate is the evidence integral. So you remember from yesterday that the posterior probability is the prior times the likelihood divided by this normalization constant that we mostly get to ignore in MCMC. And this thing right here, which is sometimes called capital Z, is the thing that nested sampling is designed to evaluate. And this is the integral of the numerator, right? It has to be this whole thing has to integrate to 1, so the denominator has to be the integral of the numerator. And so this thing's super hard. Like, I try to always avoid ever computing this if I can. And most of the time I can. And I sort of, one of my jobs in life is to consult people on ways that they don't have to compute this even when they think they do. anyway, that's an aside. But nested sampling, for better or worse, is designed to compute that integral. And it turns out that as a byproduct, it also produces samples from the posterior. So it will also generate the samples that we want to do the integrals that I've been talking about so far. And sort of schematically, the way that this works, I'm going to redraw that multimodal posterior. Let's say that, so we have a posterior, or let's say, okay, so let's say we have a likelihood function that looks like this. This is the likelihood function. And we have some prior that's like a top hat in some range. This is our prior. The way that nested sampling works is it generates samples from the prior under a constraint that the likelihood is larger than some value. So what that means is you draw a line across here, and you generate samples from your prior, which in this case is just uniform, and you accept those samples if the likelihood at that point is higher than the threshold that you set. And in practice, the way that you implement that is you start with low values of that threshold, so you accept basically everything, and then you step that up through here until you sort of are just getting the tips of that. And with some math, you can work out how to compute the evidence integral that you want from the results of that process. But one of the things that's cool is that if you can figure out how to implement it, which some people have, you actually can deal with these multimodal distributions very well, because if you're sampling from the prior, you're going to find both of these modes if you're sort of sampled densely enough. And then as you go up, you're still going to get samples in both of those modes. And so if you have a multimodal distribution, nested sampling is really very great. And so one of the reasons why I wanted to mention Dynasty is that it's the first example of nested sampling that I've seen that's very easy to install in Python. There might be others, but this is the first that I'm aware of. And it sort of has a very easy to use user interface. And it's sort of pure Python, and it was written by an astronomer. And the interface is actually very similar to MC. So if you have something written in MC, it's actually very easy to switch it over and try Dynasty. And that's one of the things that we're going to talk through in the tutorial. So a few things about Dynasty. So it solves some of the problems that we talked about with MC. So one of the problems, it doesn't require an initial guess. So it starts by sampling, it starts by sampling from the prior, and then it restricts this likelihood, and it's going to find the posterior mass. And so it doesn't require that. It also can handle multimodal situations like this in a way that MC like super cannot. Now, one thing that it doesn't do very well is it doesn't scale to high dimensions very well. So again, there have been some ambitious applications of nested sampling, but most of the time you're limited to about tens of parameters. And so if you have many more parameters than that, then Dynasty probably isn't the right choice. Another thing that I would say that I don't have like great proof for, but some experience with is that since it's solving this harder problem over here of computing that evidence integral, it can be less efficient than an MCMC sampler if you have a well-behaved problem with a good initial guess. And so it's worth comparing the different methods depending on your particular problem. But overall, it seems very promising. It's just been out for, I don't know, a year or something like that. Definitely worth checking out. Any questions about Dynasty? Yep?
So one of the things with MC, when it finishes a run and you're kind of looking at the diagnostic and making sure that your likelihood isn't changing anymore as a function of time and everything is kind of flat and converged and everything. I've noticed, with Dynasty that, your likelihood is always increasing by definition, basically. So kind of, is there a sort of different mental thing that you adopt when you're deciding whether a Dynasty run has sort of successfully done what it needed to do?
Great. Yeah, so that's a great question. So I have a lot of experience with judging convergence of MCMC. I'm kind of a noob when it comes to nested sampling. So one of the things that I was very impressed with Dynasty is that there are a lot of convergence diagnostics built into it, and so you don't actually choose the number of steps that you want to do. You choose a threshold for how accurately you want to estimate the evidence integral. And so it's doing those calculations behind the scenes of, sort of what's the effective sample size and things like that. So I don't actually know very much about how you should adjust those parameters depending on your needs. And so I'd say, check out the documentation, and there's a really nice paper about it. And I don't really know the answer there. Any other questions? Good. Oh.
Can you just quickly speak to the speed of Dynasty? So let's say similar problems that can it be parallelized?
Sure.
Versus MC?
Yeah. So Dynasty can be parallelized very efficiently because you have sort of parallel. You have parallel live points in the same way that you would have walkers in MC. So a lot of from that perspective, you get computational efficiency there. As far as test problems, you can come up with examples that are better for either. So I don't sort of have I can't say it's always going to be better to use one or the other. For sure, if you have a multimodal problem that you're working on, Dynasty will be better than MC. But otherwise, I think it's sort of a trial. It's worth playing around with. And one of the things that I'm hoping to show is that it's actually super easy to translate between the two. So it's not too hard to try both of them. Good. Okay, so the last one I wanted to talk about is PyMC3. And so one of the things I was going to say, which is obvious but worth mentioning, is that one similarity between MC and Dynasty is that they're both written by astronomers, which has its pluses and minuses. One of the pluses is that our email addresses, and I'm not great at responding to email, but probably Josh is very good at responding to email, and I try. So that can be great. PyMC3 is not written by astronomers. There have been some contributions from astronomers, but it's not written by astronomers. It's also a much bigger project, so there's a large number of contributors to the code base, which is great. So it's sort of a much bigger community, and lots more people use it in other fields. There are various reasons that I will only have time to touch on very briefly for why it's not widely used in astronomy. But I'm very excited about it. I've been using it almost exclusively for lots of projects that I'm working on because the real benefit, the thing that matters, is that it scales very well with the number of parameters. So like if you have hundreds of parameters, thousands of parameters, no problem. You can do MCMC using PyMC3. That comes with its own set of issues. But that's the benefit. This is why you care about PyMC3, because there are lots of problems that you're going to be working on that have more than 10 parameters, okay? I said that, so I won't have time to go into the details of the algorithm behind this. It's this method called no U-turn sampling, and there are lots of resources online that you can look at about sort of giving you some idea of what's going on there. But I wanted to just give a quick intro to a related method that's much easier to explain, and I might even be able to do in 4 minutes, although we'll see. But basically, the idea is, so the method that I want to talk about is Hamiltonian Monte Carlo, and it's sort of the precursor for something like no U-turn sampling. And basically, the idea there is, I'm going to yet again draw the same picture that I've drawn a million times. So let's say we have some probability density, some posterior probability, and let's take the log of it. And that kind of looks something like this, right? Now, what happens if we multiply that by -1? Seems you can't stop me. I always loved it when my quantum mechanics teachers said that, so now I get to say it. And now, what does this look like? This looks like a potential energy, right? Yeah, we're all physicists, right? That's what they think. And so if we call this, say, U of theta, the negative log probability, we're now imagining as a potential energy. Now let's say just, because I'm masochistic, I want to double the number of parameters in my problem. And I'm going to call those phi. And those are going to be, instead of having like a complicated probability density like this, they're going to be drawn from a normal, just a Gaussian. And the log Gaussian for that, so I would have P of phi, and that probability is phi transpose M inverse phi, where M is the covariance matrix of the Gaussian that phi is drawn from. Now, sorry, that should be log. The log probability for the Gaussian is this right here, okay? Now, so I've doubled the number of parameters, and I've added these two things together. So now I have log P of theta and phi, minus is U of theta plus 1/2 phi transpose M inverse phi. Now, if you look at this, if that's a potential energy, what's this? This is a kinetic energy. And now we have a Hamiltonian. This is the Hamiltonian of phi and theta. And it looks like we haven't done too much except make our job a lot harder, because remember I said all these methods scale poorly with the number of parameters, and now I've doubled that, so that's bad news, right? But no, it's not. It's actually great news. And the reason why is that when a physicist looks at a Hamiltonian, or at least some, I don't know, it's been a long time. But what they would do is they would realize that you know how to integrate that Hamiltonian. So you know how to integrate that Hamiltonian in time. And there are two things about that. So first of all, remember for MCMC, we need to make a proposal that's reversible. And so if you integrate your system forward in time, you should be able to integrate that system backwards in time and get back to the same location. So that sort of hand-wavy style satisfies one part of what's required for an MCMC step. And so then the crazy thing that I'm going to say is that why don't we just try having this high-dimensional space, and we're going to do leapfrog integration and integrate this system from some set of coordinates, theta phi. I'm going to integrate that to some theta prime phi prime at later time. And then I'm going to do Metropolis Hastings accept reject on those new coordinates. Now, remember that to do the accept reject step, the thing that matters is the difference in log probability, which in this case would be the difference in Hamiltonian, or the difference in energy. And so that means that if we integrate our system conserving energy, then our acceptance probability will be 1. We're always going to accept any proposal that we make. And that's the thing that's crazy about Hamiltonian Monte Carlo, is that doubling the number of parameters ends up giving you a much more efficient sampler that doesn't, you don't have an acceptance probability of 20%, you have an acceptance probability of 100%, and you're able to move further in parameter space. And so in practice, you end up with much shorter autocorrelation times and much more efficient sampling. Now the catch, before I finish, is that you might remember that in order to integrate a system like this, you need to be able to take the derivative of the potential energy and the derivative of the kinetic energy with respect to their coordinates. And so what that means is that we need to know d log posterior probability d theta. And that's the reason why this hasn't been widely used in astronomy, is that we're not very used to computing this gradient right here. And so that's the thing that really it is the tricky part of it. Yeah, question right here. I think we got the one at the back first.
Oh,
yeah,
sorry.
Great.
I didn't see there's someone else.
Yeah, no, please, go ahead.
Does this derivative have to be exact, or can it be done numerically?
So in practice, it has to be exact. I mean, there are some ideas about how to use noisy estimates, but for the types of methods that we're talking about here, it has to be exact. Otherwise, you get very bad performance. And part of that is just that your acceptance probability would drop really quickly because it's hard to conserve energy. Yeah.
So I guess it's sort of a follow-up question.
Yeah.
You say we're not used to, but it's like not able to in a lot of cases, right? I mean, because there's like whole different set of like if you're in the phase of doing optimization, there's a whole different set of algorithms that work for black box optimization versus where you know the gradient. You get like much nicer optimization when you know the gradient.
That's right. Yeah. The point there is that this also will help for optimizing if you know how to compute this thing, and the sub point was maybe you can't compute this. Maybe it's just not defined, and it's actually pretty rare. I mean, we can come up with examples where this isn't defined in ways that matter for the types of things that we want to do. But in practice, most of the time, it's just hard to compute this for real software. I'm happy to talk about this offline because we're already way over. And the key word there is automatic differentiation or backpropagation, and that can be applied to a whole lot of different applications. So the way that PyMC3 deals with this is that they've written their own like weird modeling language that you have to learn in order to use it, and that modeling language knows how to propagate all the derivatives through. And so that's annoying. You can't just it's not easy to translate code from MC to PyMC3 and things like that. But it's super powerful. So I'm hoping that you'll get a chance to play around with that a little bit in the tutorial. One more question at the front here, yeah?
Yeah, I was just, I think there's a bunch of these languages that have been built recently, like, obviously Torch can do that, and
yep.
Like Jax is
Jax,
talking
yeah.
about being able to do that with
yep.
arbitrary Python functions. So
that's right.
These people aren't converging on, it seems like right now we're in the explosion of differential, but so they have their own, is what you're saying. Though.
So this one is, PyMC3 is built on top of a framework called Theano, which is it was like one of the early versions of these things. It's actually been deprecated. And so, there are lots of reasons why you might prefer something like TensorFlow or PyTorch or Jax or Stan or, there are all of these other options that exist now. I have stuck with PyMC3 because it still has the best inference capabilities of any of of any of the other options, or sort of it has the best compromise. But yeah, there's a lot of sort of future potential there. And that's a big question that is open in the PyMC3 community about what the future is. Okay, so I'm going to cut it there. And I have a super long notebook as well that we get to work on after, I think it's break now, or are we right in? We're just going straight to the, awesome, great. So all those things. So what I, do you want to say something?
Yeah.
Yeah.
So
go.
First off, let's thank Dan for a very nice lecture.